So this is the first question on the Thermochem Check-in that I assigned. And I'm just doing this so that people who miss the class will be able to see how the question is done, particularly because this question relates directly to the labette that we just did, because it's the exact same set of reactions. And so if we look at the question says, according to this information and given the fact that water, delta HF, equals negative 286 kilojoules per mole, what is the delta HF for magnesium oxide? And that's a solid. And then it gives you these two reactions that I've already written out. And so we have to calculate the delta H for the overall reaction, and we're going to do that by using Hess's law. And so the first thing that we need to do is figure out what is our overall equation. And it asks us to find the delta HF for magnesium oxide. So the overall equation is going to be the formation of magnesium oxide. So magnesium oxide formation looks like magnesium solid plus oxygen gas. It's going to give us magnesium oxide. And then we want to make sure that we balance this equation, so we're going to put a half in right here. So that's the overall equation that we are looking for. But if you're looking at this particular example, what you'll notice is, if you go back through the two equations that exist here, you're going to find that we're trying to find magnesium oxide. It appears right here in this equation, the second equation. But some other things appear, and we have no way to cancel them out. For example, there's water here in the second equation, but there's no water in this first equation, and there's no water in the overall reaction. So we need another reaction, and the clue to which reaction that is given in the question. And it tells us that the delta HF, so the enthalpy of formation, for water is negative 286 kilojoules per mole. So we need to write the formation of water. So hydrogen gas plus 1/2 O2 gas gives us water as a liquid. So, and then the delta H is negative 286 kilojoules per mole. How did I know that was the equation? Well, it tells us it's a formation reaction because it gives us the enthalpy of formation. And formation, remember, means that a compound is formed from its elements in their standard state, and it has to be for 1 mole of that compound. So that's why I included this reaction. This reaction is going to allow us to now rearrange these equations and use Hess's law to find the overall delta H value. So we want to look at our equation here. So we're trying to find magnesium solid. And when we're looking at our overall equation, we should then look back to our original equations and see, is magnesium solid anywhere here in this particular, these three sets of reactions, sorry. So it's in the first equation, it's a reactant in the overall equation, it's a reactant here in equation 1, and I'm just going to go ahead and number these equations to make this a little bit easier. Oh, you can't see that. There, that makes it a little bit better. Okay, so notice that here in equation 1 we have solid magnesium. Here in the overall equation we have solid magnesium. This is a reactant, this is a reactant. So I can go ahead and check this one off. I have solid magnesium in the place that it is supposed to be, and it has the correct coefficient. This is a 1, this is a 1. There's no 1 there, obviously, but we know to include the 1 in our brains, right? We know that. Okay, so moving on. The next thing we're going to look for is the 1/2 O2. So the 1/2 O2 is going to appear in equation 3, and so we know that here in equation 3, it's a reactant in the overall equation. The coefficients are correct, so we can just check that one off. We don't need to rearrange equation 1, and we now don't need to rearrange equation 3. So then we're going to look for the solid magnesium oxide. The solid magnesium oxide appears in equation 2. You'll notice that in equation 2, it is a reactant. And so in order to fix that problem, we're going to have to do a little reversing. So here it's a reactant, here it's a product. I need this to be on the product side, so I'm going to reverse the equation. So I'm just going to cross it out and rewrite it at the top, because why not? So MgCl2 aqueous plus water gives us MgO solid plus 2HCl. And now, because I reversed the equation, this had been a negative 151. It now becomes a positive 151 kilojoules per mole. And so magnesium oxide is now on the correct side of the equation compared to where it was. So from here, we should be able to cancel out things that appear as both reactants and products. So when you're looking at this question, we see that, oh, that shouldn't have been a 2. That was my mistake. Sorry about that. All right, we see that H2O appears as a reactant here, and it appears as a product here. So I'm going to go ahead and cross those out. We see magnesium chloride appears as a reactant here and a product here. Cross those out. So when they appear on both sides of an equation, then they're really not part of the equation anymore. So I'll cross out HCl, and I'll cross out the hydrogen gas that appears in 2 equations, once as a product and once as a reactant. And then that leaves me with magnesium plus 1/2 O2 gives us magnesium oxide. And so we know that we've rearranged the question or the equations correctly, and now all that's left to do is add our delta H values. So I can add 151 minus 467 minus 286, and that should give me 602 kilojoules per mole, which is the theoretical value for the formation, the enthalpy of formation of magnesium oxide. I hope this helps. It should help you with this question, and it should also help you with your labette number 2.